Good morning.
Good morning, sir.
Yeah, so welcome back to another session on digital image processing. Uh, we will quickly review what we did in the last class and continue today's content. Okay, is the slides visible?
Yes, sir.
Okay. Yeah, so we tried understanding image transforms. We understood that it is going to take image from spatial domain to transform domain. And we also saw what is the advantage in doing image transforms. It could be in terms of reducing the task of some operations in spatial domain, or maybe the complexity, then increasing the speed of computation, particularly convolution and correlation, and representing the data in compact form. These are the three advantages when we take image from spatial domain to transform domain. We also saw various categories of image transforms and depending on the basis function that we are going to use. And we tried representing the transform in the form of a matrix computation. So forward transform would be to multiply the data in time domain or spatial domain with a transformation matrix A. And depending on the characteristics of this A or property that is satisfied by this transformation matrix, we classified transforms into what is known as unitary transforms. So a transform is said to be unitary if the matrix A is unitary, and we also saw the condition for a matrix to be unitary. A into A Hermitian should be an identity matrix, where A Hermitian is the complex conjugate transpose of the matrix A. And to get back your U from V, we can just perform the inverse operation. And doing inverse operation on a big matrix is difficult. So if the matrix satisfies unitary property, then such a transform will be unitary transform, and inverse would be calculated by just doing A conjugate transpose. That means Hermitian. This is what we understood. Suppose if the matrix is real, then the transform is said to be orthogonal if the matrix satisfies the condition A into A transpose is identity. This is for real transforms. We will take examples of each one of them in the next few minutes. So this is about one dimension, how we can represent forward transform and inverse transform. But as I told you in the last class, we have to discuss this in the context of images. That means we need to do two-dimensional transforms. So how do we define 2D unitary transforms? So here your image will be of size n cross n, and this is the formation. Just compare this with the one-dimensional equation. So here there is a single summation and you have a one-dimensional signal here, and there is a basis function which depends on k and n. So here there would be a two-dimensional signal. So your image is two-dimensional. This is the two-dimensional signal u of m comma n. You will have two summations because I have two variables m and n, one along the x direction, one along the y direction. Then you will have the basis function now, which is a function of four variables. Here the basis function is depending on two variables, one transform domain variable and one time domain variable. N is the time domain representation and k is the transform domain. Whereas now your image itself has got two dimensions. So m and n is the spatial domain variable. K and L will be the transform domain variable. That is why you have totally four variables now. M, N in the spatial domain, K and L in the transform domain. So your basis function will be depending on all these four parameters or these four values, variables. And of course, inverse Fourier transform, as we saw, inverse transform, we can write it in terms of u of mn on the left hand side. Just compare it with this equation. Here it is one dimensional inverse transform, here it is two dimensional. So there are two summations. Summation is for the values of k and l here. V of kl is the transform domain representation, and we saw that a see the basis function will be the complex conjugate of this. Again, uh, this is similar to one dimension, and why this complex conjugate exists you also know in with an example of Fourier transform. Okay, now there is a very important property of 2D transform. I'll justify this with an example of Fourier transform later. 2D Fourier transform. As I said, basis function. In fact, now it is called a basis image actually, because it is an image for an image. So it depends on k, l, m, and n, and this function, if it can be separated into two one-dimensional functions. Carefully observe, this is a two-dimensional function, which is now written as two one-dimensional functions. So if I can separate it into two one-dimensional functions, then this could be utilized in making our transformation simple. So if I use this, if this condition is satisfied, again with an example, I'll justify it in the next few minutes. So I can just write this as AKM and ALN, okay, or of course I can write it as BLN also. But since they are similar, we are using the same notation. So this two-dimensional forward transform can now be represented in terms of the matrix multiplication. U is your original image. A is actually the one-dimensional uh, transformation matrix, which we have written it here already, this A. And A transpose is the transpose. What I want to convey here is, if the transform satisfies a property called separability, then I can write the forward transform equation by using the one-dimensional transformation matrix. So even though the image is two-dimension, I can evaluate two-dimensional transformation by using one-dimensional transformation matrix. Okay, we'll take a simple example and justify this. This is for forward transformation, and similarly inverse transformation can be written by using this equation. So just see, it is similar, there is no difference at all. A transpose V, but here it will be A conjugate transpose V A conjugate, because this is for image, this is for a one-dimensional signal. That's all the difference. Okay. Now here we don't use basis functions, we use what is known as basis images. This can be determined by using actually what is known as the outer product of the columns of A conjugate transpose. Again with an example, let us justify this. Okay, so let me just now go back to the OneNote and write. Okay, so is my OneNote visible? Hello. Is the OneNote visible to you?
Yes, sir, visible.
Okay. Now, before we actually go to the discussions, let me just give you, because now we need to know about the properties. So let me just give you a simple problem to start off. Okay, the problem is check whether the following matrix is unitary or not. Okay, the matrix is A, it is 1 by root 2 into 1 j, j and 1. Okay, yeah, this is just to uh, understand what is the meaning of unitary matrix because we are going to use it. Okay, can somebody tell me what is the procedure to verify a given matrix unitary or not? In the last class we have discussed. If you want, I can show that to you. Okay, so yes, a matrix. Yes, yes, somebody is trying to speak. Is it Vinay Kumar? Okay, so if none of you are speaking, let me just continue. So if the matrix is unitary, then the condition is A into A Hermitian should be identity, where A Hermitian is A conjugate transpose. So first let us find A Hermitian, which is nothing but A conjugate transpose of that. So I'll just find A conjugate. How will you find A conjugate? You have to replace J by minus J. That's all. So this is 1, this is minus J, this is minus J, and this is 1. This is how I can find A conjugate. A conjugate transpose means rows should be replaced with columns. So that is easy. But in this case, since the matrix is symmetric, uh, in fact, you will get back the same. But this is not true always. Be very careful. Okay. Now what I have to do, I have to just multiply A with A Hermitian. So that means 1 by root 2 into 1 J J1 into 1 by root 2 1 minus J1. Okay. So 1 by root 2 into 1 by root 2, I can write it as 1 by 2. Now I think you know matrix multiplication. So 1 into 1 is 1. J into J is J square with a minus sign because here there is a, so it is minus J square, and you know J square is minus 1. So I'll actually get it as 1 plus 1 here. 1 into minus J plus J into 1, it gets cancelled. You will get a 0 here. J into 1, 1 into minus J, it gets cancelled. It will get a 0 here. J into J is J square, which is minus 1. Minus into minus is plus 1. So you will get 1 plus 1 here. So this is 2002 divided by 2. So I'll get 1001. Is this clear? Which is an identity matrix. Any doubt? Any doubt? We speak.
No, sir. No, sir.
So I can conclude and say A is unitary matrix. A is unitary matrix. Now let us take a second problem just to verify. This has to be done by you. Okay. So here A is uh, 2 J minus J root 2. Okay. This I can you can do it later. I will give you the answer so that you can verify it later. This is not unitary. That means it will not satisfy the property. Okay. I expect you to do the problem later, not now. Now the third one, that is also check orthogonal property. Check whether A is orthogonal or not. And you know, this is defined for real matrices. So your A should be a real matrix. This you can probably do it now only. In fact, you are going to see this matrix again and again in this particular top unit. So can somebody tell me what is the condition for a matrix to be orthogonal? Hello? What is the condition for a matrix to be orthogonal? A matrix A is said to be orthogonal if A into A transpose is identity. So in this case, A into A Hermitian is identity, but here A into A transpose is identity. Because the matrix is real, therefore A conjugate will be itself, so it satisfies the condition. So A into A transpose should be equal to identity. This is a condition I have to verify, and you can observe here A is a symmetric matrix here. So in fact A transpose is itself 1 1 1 minus 1 1 by root 2 1 1 1 minus 1. Now if you actually try solving this and multiplying, you will actually get it as 1 0 0 1. You can verify it. So A is orthogonal, that is the answer. A is orthogonal. Okay. Now I will give you a problem. This is not on checking the orthogonality. The next problem is using the transformation that I just explained. Okay, using this. So you have a two-dimensional signal, and you have a transformation matrix to be given to you. So I will give you this. I want you to find V. Of course, I also want you to find U back from V. Okay, so let us do that. This problem is very popular, so please concentrate. For the given orthogonal matrix, A, which is given like this, it is same thing. In fact, whatever we have just now tried proving it. 1 by root 2, 1, 1, 1 and minus 1, and image U. Image U is 1, 2, 3, 4. This is an image. So it's a 2 by 2 image. The problem that is given to you is find the transformed image V. Find the transformed image V. That is the first thing. The second one is find the basis function. In fact, basis images here. I'll explain how to do that. Third one is verify your result. Okay. So I'll solve the problem. Please observe carefully, and this is a very important problem. So as you saw here, V can be determined by using the formula A into U into A transpose. Okay, so let us use this and solve it. So V will be equal to A into U into A transpose. Now here A is 1 by root 2, 1, 1, 1 and minus 1. U is 1, 2, 3, 4. And A transpose is, in fact here this is a symmetric matrix, so transpose is itself. Okay. This is a simple matrix multiplication. Just for saving time, I'll not do the steps individually. I'll give you the final answer. You can verify it later. You will get this as 5 minus 1 minus 2 and 0. That means if you multiply these matrices and okay, use the values 1 by root 2 and 1 by root 2, multiply these three matrices, you will get back this answer. Okay, please check this, you will definitely get this answer. Okay, so this will answer my first question, finding the transformed image v. So what you have here is the transformed image. Okay, the next is finding the orthogonal basis function. So just observe here, I have introduced that basis images can be found using the outer product of the columns of A conjugate transpose. So let me go to A conjugate transpose. In fact, A is a real matrix, therefore conjugate is itself. A is a symmetric matrix, therefore A transpose is A. So let me just write it again. A conjugate transpose will be, for this problem, don't think this is always true. For this problem, A conjugate transpose is A itself because it's a real matrix. Transpose, it is also symmetric matrix. Okay. Now, outer product is this. Actually, if you multiply, okay, so let me just take the first one. Suppose if I want to take the first column, 0th column, I have to take the outer product of 0th column with itself. Okay, so the outer product can be written like this. So the first column is 1 by 2, 1 and 1. Outer product means you have to take the transpose of this. This is the outer product. That means if I have a matrix like this, outer product means you have to take the first row, first column, and write the first column and take the transpose of the first column, which becomes a row, then multiply these two. That's what it means by outer product. Okay, inner product, I think you know, inner product will actually give you a scalar quantity, outer product will give you a in fact a matrix here. So now this would be, this is equal to, what do you get? I'm sorry, this is 1 by root 2, sorry for that, this is 1 by root 2. So 1 by root 2 into 1 by root 2 is half. So outer product, 1 into 1 is 1, 1 into 1 is 1, 1 into 1 is 1, 1. I hope you understood this. This is the first basis image. This is the first basis image. Now the second basis image is, I'll take the first row and first column and second column and take the outer product. So the first column is 1 by root 2, 1 and 1, and the second column I have to take the transpose of it. It is 1 by root 2, 1 and minus 1. So this I'll get it as 1 by 2 into 1 minus 1, 1 and minus 1. So this is the first basis image. This is the second basis image. Similarly, you can do the third one, 1 comma 0. That means first column and with 0th column. Take the outer product. So outer product, as I told, column write it as it is. So first column is 1 and minus 1. The next second one you have to write the row of it. So second column is 1 and plus 1 here. So this is again half into 1, 1, minus 1 and minus 1. This is the third basis image. See, if there are any doubts, please ask me. I'm trying to go as slow as possible because this is an important problem. Lastly, I will take the first column with the first column, outer product. So 1 by root 2, 1 and minus 1, 1 by root 2, 1 and minus 1. you multiply them, it is half 1 minus 1 minus 1 plus 1. This is the fourth basis image. Okay, so you have a 2 cross 2 image, so you will have 2 into 2, 4 basis images. That's what is the second one. Okay, now what this tells me is, if you go back to my representation, see, when I want to get back my original image, I have to actually multiply the Fourier or the transform coefficients with the basis images. So when I multiply the corresponding basis image with the coefficient, I'll get back my u. So let us do that. That is actually the verification that is supposed to be done. That is the third one. Verify your result. Okay. How will I verify? My u can be obtained by multiplying the first coefficient. What is the first coefficient? Observe. The first coefficient you can observe here. 5 is the first coefficient with the corresponding basis image. Okay, so 5 into 1 by 2, 1, 1, 1 and minus 1. Minus 1 or plus 1? Plus 1, sorry. This is plus 1. Okay, then plus, what is the second coefficient? That is this. So it is minus 1, which is 0th row, first column. So the second coefficient is minus 1 into the corresponding basis image, 0th row, first column. That is this, which is half into 1 minus 1, 1 minus 1. So this is into half to 1 minus 1, 1 minus 1. Plus the third coefficient is minus 2. You can observe here. It is minus 2. That is this. Into the corresponding basis image, which is this one. Third basis image, which is half into 1, 1 minus 1 minus 1. Plus the last coefficient, if you carefully observe, it is actually 0. So it is 0 into, anyway I'll write it. I know 0 into anything is 0, but let us write it. The last one, it is half into 1 minus 1 minus 1 plus 1. Okay. Now this has to be evaluated and you should get back your original image. Okay, so this is 5 by 2, 5 by 2, 5 by 2, 5 by 2. So the first matrix is this. And here if I multiply, it will be minus. So let me write that as plus here and take the minus sign inside. So this is minus half, plus half, minus half, plus half. And if I multiply, I'll get minus 1 here. 2 and 2 cancel. So let me take that minus 1 inside. Minus 1, minus 1, plus 1, plus 1. Plus 0 into anything is 0. Therefore, it is 0, 0, 0, 0. I hope you have understood. So what I have tried here is, in this particular step, I am trying to represent the original image in terms of the corresponding basis images and the coefficients. This is exactly the concept of any transform. So carefully observe the answer now. 5 by 2 minus half is 4 by 2, which is 2. 2 minus 1 is 1. So this value is 1. Then 5 by 2 plus half is 6 by 2, which is 3. 3 minus 1 is 2. Then 5 by 2 minus half is 4 by 2, which is 2. 2 plus 1 is 3. Then 5 by 2 plus half is 6 by 2, which is 3. Plus 1 is 4. So you can observe here, you will get back your original image. Okay, that is the verification. That is the verification. This is not only the verification, I can also do one more verification. Carefully observe here. You can get U by doing this operation, A conjugate transpose V into A conjugate. So I will not completely do it. I'll just write the step. So U can also be written as A conjugate transpose into V A conjugate. In this case, since the matrix is real and also it is symmetric, A conjugate transpose is itself. So 1 by root 2, 1, 1, 1 and minus 1, and your V is 5 minus 1 minus 2 0 into 1 by root 2, 1 by root 2, 1, 1, 1 and minus 1. So if you perform this, you should get back this. You can verify it. Okay. In fact, this is this is a very important step in any transformation. How I can get the transformed image, how I can get the corresponding basis images, how you can verify that the image can be represented in terms of the basis images. So that's what we have done here. Any image is represented in terms of the basis. This is the first basis image, second basis image, third basis image, fourth basis image. So basis images for a given transform will not change. For example, if in this case, in the same case, if I give you u is equal to say some 1, minus 1, 2 and minus 2, something like this. Okay. The only change now that will be there is you will get a different V. Okay. A will be same. That means your transformation matrix is same. Only what has happened is your U has changed. Because of that, you will get different coefficients. So you have to plug in those coefficients here. Okay. But the basis image doesn't change. This remains as it is. For a 2 by 2 transformation, these basis images are same. That won't change for this particular case. Only in KL transform, basis images will change. I have told you in the beginning only. Okay. So I can represent a given image in terms of its basis images. So the only change that happens is these coefficients. Okay. So I hope I have made the point clear. If there are any doubts, please ask me. Otherwise, we'll go to the next concept. Hello, are you with me? Anybody? Is there any doubt? Shivam, are you there? Okay. So this problem is very important. Please practice it. Yes, yes, there is some doubt. Yes. Hello.
Yes, sir, I'm there, sir.
Okay,
Shivam.
okay, okay, okay. You just work. So this is how we can represent. We can use, in fact, the separability to represent any forward transformation in terms of matrix multiplication. Please note here, this transformation matrix A is one dimensional transformation. Whatever we have done here is enough. That's what is the advantage of separability. Okay. In fact, you will notice that all the transforms that we are going to study in this course, they are separable. So that is in fact inbuilt in the transforms that we are going to use. So if the separability property is used, then I can represent any two-dimensional transformation in terms of one-dimensional transformation matrix. Okay. So now let us try to see what are the properties of these unitary transforms. Okay. One of the properties is what is known as energy conservation. See, what are we trying to do? We are trying to take an image or maybe a one-dimensional data into the transform domain. So the question is whether the energy of the signal changes when I go from one domain to other domain. But in a unitary transform, that is one of the property, energy doesn't change. That means energy in time domain or spatial domain is same as the energy in the transform domain. So you can verify it also. In fact, you can verify it for one-dimensional DFT also. When I take Fourier transform of a one-dimensional data, you can find the energy in the time domain. You can find the energy in the frequency domain. Both of them will be same. If it is an image, then energy can be calculated like this. So you just square each and every value of the matrix, add them. They should be same. Let us verify it. Let us verify it for the problem which we have done. Okay. So we are trying to verify energy conservation property here. So what we did is we took an image in spatial domain and we just took the transformation. We did some transformation using a unitary transform, and the answer that we got is 5 minus 1 minus 2 0. Okay. So according to the property energy conservation property, how to calculate the energy, just observe. You have to just square each value and add all of them. So let us do that. So 1 square plus 2 square plus 3 square plus 4 square. This is the energy in spatial domain. Let me call it as ES. So this is 1 plus 4 plus 9 plus 16, which will be equal to 30. Now let us do the same thing in the transform domain. So I'll just call it as energy in the transform domain. It is 5 square plus minus 1 square minus 2 square plus 0 square. So 25 plus 1 plus 4 plus 0, which is also 30. This is one of the property. When I take any signal from one domain to the other domain, energy gets conserved. Okay. This is one of the important property because you cannot change the energy when you take the signal from one domain to other domain, because when you come back you will get a different signal. You cannot get the same signal. If your inverse has to exist, I should satisfy this condition. Now the second condition is also important. Remember when I introduced the transforms, I told uh, you can okay, have compression of data if you go for transformation. So this is studied under the heading called energy compaction. Okay, energy compaction means it is the ability of a transform to pack a large fraction of the average energy of the image into a relatively few transform coefficients. Okay, in fact it is almost verified in the first problem itself. In this problem, okay, observe here how many values are there in my image. Four values are there, correct? 1 2 3 4. There are four values. Go to the transform domain. You can observe here you have only three values now because one of them is 0. One coefficient is 0. That is why when I tried multiplying you got this as 0. So the entire energy of the signal is now in fact confined to only these three coefficients because the fourth coefficient is 0. Let me demonstrate it by using another example. I think I have written a small code here. Okay. Don't worry about what code I am writing here. I'll just evaluate it. What I have tried doing it is I am using a transformation matrix. Uh, okay. I am using a transformation matrix A, and U is an image now. It is 4 cross 4. In the previous problem we solved, it is 4 cross 4. I could have asked you to do it manually, but it takes time, so that's why I'm just doing using MATLAB. So I've just taken U and I have just generated A by some means. Let me not explain this right now, I'll do it later. So U is this is your image. I have just used A into U into A transpose, that is your transformation. This is what I got. Now carefully observe, this is 0, this coefficient is 0, this coefficient is 0, this is 0, this is 0. See, there are 16 values here, but you can observe here 1, 2, 3, 4, 5, 6, 7, almost 9 values are 0. All these values are 0. What it means, if it is enough, I store only these values. I don't need to store 16 values. 16 minus 9. 8 values if I store, it's enough. In fact, 7 values. Okay. So this is exactly what it is trying to say. Is this clear what I'm trying to explain? It's easy to remember, but I want you to notice. So it is the ability of a transform to pack a large fraction of the energy into a relatively few transform coefficients. So in the example I showed you, original image had 4 cross 4 size, whereas the for transform coefficients you only have about 7 coefficients. The remaining 9 coefficients are 0. So you can just store 7 values instead of 16 values. This is compression actually. The third one is if I have a highly correlated data, it can be in fact separated into an uncorrelated data. That is another property of unitary transforms. In fact, image is a correlated data. If you just transform it, you can make it uncorrelated, and this has an advantage. Okay. And the last property is the determinant and of course the eigenvalues of unitary matrices have unit magnitude. Okay, again this you can verify it later. See the transformation matrix here in this case A is 1 by root 2, 1, 1, 1 and minus 1. So if you find the determinant of this, you know you will get it as 1. It is not difficult. Try to find the eigenvalues of this, it will be unity. Unitary matrix will have unit. You can verify this. I will not show it now. Okay, so these are 4 important properties of unitary transforms. One is energy conservation, that means energy gets conserved when you go from one domain to other domain. Energy compaction, that means the ability to pack a large amount of energy by using few coefficients. The transforms are going to do decorrelation, and the determinant and eigenvalues of a unitary matrix will have unit magnitude. So these 4 properties are very important, which will help us in several things. One good example is compression. Okay. So in general, we have discussed about uh, transforms in general. Now we will take typical examples. See, we will now take one by one. Okay. So let us start with the DFT. And DFT comes under the heading of transforms that use sinusoidal orthogonal basis functions. So DFT is an example of a transform that uses sinusoidal orthogonal basis functions. So since you have already done DFT, I don't think it would be difficult for you to understand. Let me just go back to uh, what we did in the previous class. Okay, so this is your DFT equation. Just to make them look similar, I also told you that usually this is how the equations are represented. Instead of showing 1 by n in one equation, 1 by root n in both the equations is written. This is just a scale factor, so we are not interested in the amplitude of the signal, the frequency component. It is just a scale factor. So you will have 1 by root n, 1 by root n, a summation here, time domain signal here, transform domain signal here. This is your basis function. This is the complex conjugate of this. So that's what is being explained here. So there is 1 by root n, summation 0 to n minus 1, time domain signal and your basis function. This is the forward transform, and all of you know this can be represented as V is equal to F into U, where F is the unitary matrix. So I am now changing the nomenclature. In fact, we were using A, but you know now it is for Fourier transform, so I'm using F. If it is discrete cosine transform, I'll be using C. So just to separate them, identify them, I'm using different notation. So F is the matrix now, and that is a unitary matrix. Okay. So how do I get inverse Fourier transform? Again 1 by root n, summation. Now the summation is for k is equal to 0 to n minus 1. This is v of k instead of u of n. Instead of minus, this is plus. Okay, and as usual you can write u as f inverse v, but since it is unitary, f inverse is same as f conjugate transpose. Okay, now let us try to do this with an example. I hope I still have some time. Okay, so let us just try to. Okay, so I'll just take a DFT. Okay, the question is find the transformation matrix for say n is equal to 2, which we may do it today. For n is equal to 4, I want you to do it. I think you have done this already in DSP course, except some small change. So V of k is 1 by root n summation n equal to 0 to n minus 1 u of n into e to the power of minus j 2 pi k n by capital N. This is the equation. So let us just now try to find the transformation for matrix for n is equal to 2. How do I do that? So n is equal to 2 means your small n will go from 0 to 1. Even k will also go from 0 to 1. You know that. Therefore, let me just solve them. V of 0 is 1 by root 2 summation n is equal to 0 to 1 u of n e to the power of minus j. Since k is 0, this will be e power minus j 0. So this is equal to 1 by root 2 into e power j 0 is 1. Therefore, it is u of 0 plus u of 1. This is the first equation. Okay, now v of 1, because k can take value equal to 1, so this will be equal to 1 by root 2 summation n is equal to 0 to 1 u of n e to the power of minus j. Now k is 1, so I cannot write it just like that, so it is 2 pi into n by 2, n capital N is 2. So now put the value n, it is 1 by root 2. When n is 0, this term will be 0, so it is u of 0. And when n is 1, it will be u of 1. What will be this value when n is 1? 2 2 cancel, so it is e to the power of minus j pi. What is e power minus j pi? E to the power of minus j pi. Can somebody quickly tell me what is e power minus j pi?
-1.
Minus 1, correct. So this will be minus of u of 1. So I got two equations. So I can now represent v of 0, v of 1 in the form of a matrix multiplication, which is equal to okay. So since 1 by root 2 is common across all the values, I'll take it outside. So this is u of 0 plus u of 1, therefore this will be 1, this will be 1. This is u of 0 minus u of 1, therefore this is 1 and this is minus 1. So this is your transformation matrix. I'll just call it as F only because I'm using F for Fourier transform. So this is the matrix. Remember, we have already used this. That's why I told you again and again you will be getting. This is the DFT matrix for n is equal to 2. Okay. So for n is equal to 4, I want you to do it. In the next class, I will give you what is the matrix, but I expect you to do it. Okay. normally the question continues. It is not just stopped at this stage. Find the transformation matrix for n is equal to 2. Then they'll ask you, okay, show that it is unitary. Okay, this would be the question. Okay, how will I show that it is unitary? In fact, in this case, I have already verified because we have done this problem already. I think in the previous page itself it is done. Yeah, so in fact, it is even if I use A conjugate transpose also, since it's a real matrix, it will be verified. So what you meant by verifying is you have to just use this equation. Let me just write it. Verification means A into A Hermitian has to be equal to identity. This has to be verified. That's all. Okay. So I want you to actually for n is equal to 4, please find this matrix. So you'll get a 4 cross 4 matrix, and you have already done it in DSP course, except that the constant will be slightly different. Okay, because in DSP the equation that you have used will not have any constant here. It will be shown in the inverse transform. I hope you remember. So here that is the difference. So for n is equal to 4, please do this and also verify that it is a unitary matrix. In the next class, I will probably ask some of you to tell me how you have done it. Okay, so I think with this, yeah, it's time for us to wind up. Before that, let me just take your attendance. Last class I didn't take it. Okay, I think some of you are chatting on the chat window, but once I go to the slide mode, I'm unable to see the chat. I think Rakshita has given some, Bhima Shankar has given some answer. Uh, it's very difficult for me to go back to the chat window. So the attendance can be given now. Uh, Meanwhile, I just want to check. I think 4 of you have not given the certificate. So please make sure that you will give the certificate. Send the certificate to me immediately. Ramya, yes, are you there? Ramya,
Yes, sir.
you have not sent your certificate, I believe.
I have completed, sir. I will send today.
Okay. Then Rekha C. Rekha, you are also there. You have also not submitted. Bhima Shankar, you are there. I, you are not submitted. Praveen 407. He is not attending classes. I have seen. Praveen, are you there? Praveen, I think he is not there. So, okay. Bhima Shankar, what's your status? You can chat now. I can see. Bhima Shankar, what stage are you? If you cannot speak, you can chat. Okay, so you'll send it today. Okay. Yeah, this Praveen, I don't know what is the issue with him. He's not attending the class. Okay, then. Those who have completed the attendance, you can leave.